Alright, welcome to my AE3201 Astronautics project. Today, we will discuss about the reconstruction of Juno space mission. My name is Fahmi, student ID number 1361815 from Aerospace Engineering, Bandung Institute of Technology. These are the content of this presentation. Their overview, assumptions, factsheet calculation, and results. This is the overview of Juno space mission. Juno is a NASA space probe that is orbiting Jupiter planet. It was launched from Cape Canaveral on August 5, 2011. The probe was launched with AE3201 rocket and second-stage Centaur. Juno cruised in heliocentric orbit and performed a DSM to return into Earth orbit to gain a gravity assist. Using the gravity assist, Juno began to the quiet cruise phase to the Jupiter orbit, and then it arrived into Jupiter orbit and currently orbiting in elliptical polar orbit of Jupiter. These are some assumptions that are used in this project. The first one is the orbit of all planets are assumed to be circular orbit. Only Juno's heliocentric orbit that are elliptical. And then the specific impulse of rocket propulsion is assumed to be constant at sea level, and so does the gravitational acceleration, equal to 9.81 meter per second square. And then there are some geometric approximation used. This is the overall reconstructed Juno mission trajectory. And then this is the fact sheet, calculation, and result. The fact sheet shows some data that are used to reconstruct this mission. The first one is about the launch site. Juno was launched from Cape Canaveral Space Station in Florida, USA. And the location is at latitude of around 28 degrees north. And then this is the fact sheet about the launch vehicle. Juno was launched atop of AE3201 rocket. It has the first stage of AE-CCB, second stage Centaur, and the Juno itself is using the Laros 1B propulsion. These are some propulsion facts about the rocket booster and Juno propulsion. And then this is the fact about the parking orbit. I assume the Juno to be parked at geosynchronous orbit with altitude of around 35,000 km above the Earth, and unfortunately I could not find any data about the inclination. And then Juno escaped from the Earth orbit using hyperbolic escape trajectory. The hyperbolic trajectory is calculated by defining a heliocentric orbit with perihelion around the Earth and a given aphelion at 2.26 astronomical unit. The hyperbolic escape is propelled by using the second stage Centaur. And then these are the perihelion distance and aphelion distance. Then, using the following set of equations, the orbital characteristic can be calculated. These equations is derived from Fish-Viva integral. There are A or semi-major axis, there are v square or velocity square, and then the distance from sun or planet, and then the time period, and the fuel mass consumed. The results here. There are the velocity infinite or hyperbolic velocity, and then circular velocity at parking orbit, and then the speed increment to enter hyperbolic escape trajectory. There are also reduced energy and propellant mass used to escape from the Earth into the hyperbolic trajectory. The heliocentric trajectory is divided into two phases. The first one is from the hyperbolic trajectory escaping the Earth, doing DSM, and then returning to the Earth. After returning to the Earth, Juno gained a gravity assist, and then using the second heliocentric orbit to Jupiter. These are the result of Juno heliocentric orbit. There are the launch date, the first perihelion distance, until the arrival date at Jupiter. These results also calculated using the previous equations that are derived from the Fish-Vival integral. And then at the arrival at Jupiter, Juno was accelerated due to the Jupiter gravity, and then entering the orbit of Jupiter in hyperbolic trajectory. The spacecraft then burned some propellant to make an elliptical orbit around Jupiter. These are some data that I calculated at the arrival of Juno at Jupiter. There are arrival speed, and then Jupiter's circular orbit velocity, hyperbolic velocity, insertion energy, and then change of velocity in Jupiter orbit insertion, and then the propellant mass used to enter the orbit. The reconstructed data then compared with the real mission data. There is the mass of propellant used in second Centaur. And then there are some data about the Juno spacecraft. There are DSM distance from the Sun, total mission time, and total propellant mass. Based on the comparison, the reconstruction can be concluded to be quite accurate due to the small error of mission time. I calculated the mission time to be 1,662 days, meanwhile the real mission took 1,791 days. There is 7.2% of error there. And meanwhile, about the total propellant mass, there is a significant error. This is due to the assumption that I use. I assume that the specific impulse is constant, and so does the gravitational acceleration. Meanwhile, in the real condition, the gravity varies about the altitude, and the specific impulse vary with the gravity, and both of them make my calculation of total propellant mass to be not accurate. The last one is reference that I use. Mainly, I use reference from Wikipedia. That the data at Wikipedia is sourced from the NASA, and then I also use data from spaceflight101.com. So, thank you for watching my presentation project about Juno reconstruction. See you.